Okay, up to this point, we've talked about combining orbitals, but only within the same atom. So going back to hybrid orbitals, we talked about combining two orbitals in the same atom and making these hybrid orbitals that were new orbitals. And then we talked a little bit about how those orbitals on one atom would overlap with another. But we didn't really talk about what those new combinations would become. And so atomic orbitals reside on one atom. What we're going to talk about today a little bit is molecular orbitals, which would be molecular orbitals are orbitals that are made by combining atomic orbitals on neighboring atoms. And when we combine two orbitals, we've talked before about how you can combine them in two different ways. What are the two different ways we can combine two orbitals? Or the two different kinds of overlap they can have? Constructive or destructive. All right. So when we bring the two orbitals together, they can either have constructive interference or destructive interference. So for example, if I imagine bringing together two orbitals, I'll make it two hybrid orbitals. And I'll have a black one and a red one. All right. If I bring together these two orbitals in that way, are they going to constructively interfere or destructively interfere? Constructively, because where they are overlapping, they're both unshaded. All right. So here, this would be in phase overlap. And when you have in phase overlap, what that means is the orbital is going to get bigger in between the two atoms. And if the orbital gets bigger in between the two atoms, that means that's a good place for electrons to be shared between the two atoms. And what do we call sharing of a pair of electrons between two atoms? A bond. So when you have in phase overlap, this creates what we call a bonding orbital. And by the way, I'll use the abbreviation MO for molecular orbitals. It's called MO theory. So this would make a bonding MO. And in the case of the two that I drew here, we can imagine the shape of that bonding MO would be something where there's lots of electron density in between the two atoms, and then just a little bit on the outside. So they come together and make this, what I think looks like a hard candy with the little wrappers on the two ends. On the other hand, we can have out of phase overlap. So if I bring those same two orbitals together, but I bring them together one shaded and one unshaded. Oops. Now we would say that's out of phase overlap. That's going to be destructive interference. And this is where it gets weird, because what's the opposite of bonding? Well, we call it antibonding. So this makes an anti-bonding orbital. In this case, the antibonding orbital is now going to be bigger on the two outsides and smaller in the middle. And it actually has a node right in between the two atoms. So if you put electrons in a bonding orbital, it tends to pull the two nuclei together. If you put electrons in an antibonding orbital, it tends to pull the two nuclei apart. Hence the name antibonding. So we end up with these two different kinds of orbitals that we can make by combining atomic orbitals. And again, you don't need to know how to draw these pictures. What you need to know about molecular orbital theory is very small. If you look at the learning objectives, there's nothing. In the entire AP course description, there's like one line. So it says, molecular orbital theory is this powerful tool, but we're not going to go into it, more or less. But I just want to give you a little background. So bonding versus antibonding orbitals. In this picture, my two nuclei would be probably somewhere around here and here. So if you imagine putting electrons in these two, in the bonding orbital, most of the electron density is between the nuclei, so it pulls them together. In the antibonding, most of the electron density is on the outside. So those electrons are actually pulling the two apart. So the name of the game, if you want to make bonds, is you need to put electrons into bonding orbitals and try not to put electrons into antibonding orbitals. More electrons in bonding orbitals will make a bond stronger. More electrons in antibonding orbitals will make a bond weaker. And I want to think for a second just about potential energy. How does the potential energy of the bonding orbital compare to the potential energy of the original atomic orbitals? Are the electrons in the bonding orbital happier or sadder? Happier. So the bonding orbital has lower potential energy than the atomic orbitals that went into making it. And the antibonding orbital has higher PE. Because the electrons are agitated. They don't get to be near the nuclei. So what we do often is we draw what we call a molecular orbital diagram that shows the energy of the atomic orbitals and shows the energy of the resulting molecular orbitals. So molecular orbital diagrams, you're not going to be required to draw in this course, but you will encounter them in the future. So the way this works is the outsides are the original atomic orbitals. So here, this would be a molecular orbital diagram for H2. So in this diagram, on the outsides, I have the original atomic orbitals, which are the hydrogen 1s orbitals. And we represent those by just a little line with arrows to indicate the electrons in them. So a hydrogen atom has one electron in the 1s orbital. That's what that's representing. What we draw in the middle are the molecular orbitals from bringing them together. So what's represented in the middle here is H2. So when I take two hydrogen atoms and I bring them together, what happens to their atomic orbitals? They combine in phase to make a bonding orbital, and they also combine out of phase to make an antibonding orbital. Where do the electrons go? So H2 is in the middle. Here are the two orbitals created. Where did the two electrons in H2 go? Into the bonding orbital. So I have two electrons in the bonding orbital. I have none in the antibonding orbital. That's what makes a bond. So when you see a diagram like this, the key is look for how many electrons go into bonding orbitals and look for how many go into antibonding orbitals. If I tried to add more electrons to H2 and give it 4 electrons, I'd have to start putting electrons into the antibonding orbital, which is going to pull the two apart and break the bond. So that's an example of a molecular orbital diagram. Yep. So the question is, there's only two nuclei. Where are the antibonding orbitals? So antibonding orbitals are around the atom. The two orbitals that are on that slide would look like this. If you drew like an electron density map for them, the bonding orbital is just kind of a big oval. The antibonding orbital is this thing with two lobes pointed outward. And they both exist in the same space. The weird thing about orbitals is you can have orbitals that like occupy the same space, which is hard for us to imagine. And it's also hard to draw. We never draw like all the orbitals at once because they're all overlapping. They're all in each other's space, and we can't represent them that well. So yeah, they're both there. Now, the antibonding orbital has no electrons in it. So you might say, well, like, how do I know it exists? And all I would tell you is we don't know that any of this exists. All of this is a theoretical model that we use. So we came up with it, and we use it for what it can explain, and for what it can't explain, we use something else. But orbital theory says that the orbitals are there even if they're unoccupied. So, in a hydrogen atom, there's also energy level 2, which most of the time is unoccupied. But those orbitals are still, quote, there in case electrons wanted to go in them. So this antibonding orbital, even though it's unoccupied, theoretically is available. If there were more electrons around, they would go into it. There might be a question on problem set 6 that asks about helium-2. Like if you tried to make a molecule between two helium atoms, what would happen? How would this picture be different if I were dealing with helium instead of hydrogen? Really? We'd have 2 more electrons, so we'd fill up the antibonding orbital. And if you fill up the antibonding orbital, that has higher energy, now you're not making electrons overall happy, and so there would be no bond. All right. Tomorrow we'll look at some more complicated ones. Okay. Hi guys. I'm going to give you the rundown of molecular orbitals. I actually already discussed this in C block. I'll give you a quick rundown, and then we'll launch into just the final 4 slides of the lecture. So with molecular orbitals, what we're doing, and don't try and copy everything down right now. With molecular orbitals, what we're doing is we're taking orbitals on 2 different atoms, and we're combining them. And when we combine them, we make new orbitals that we call molecular orbitals. And these new orbitals now are shared orbitals. So if you think about it, if you want to do bonding, you need shared orbitals so that you can have shared electrons. So molecular orbitals are made by combining atomic orbitals on neighboring atoms. And you can make them in 2 different ways. You can combine them in phase, in which case you get more electron density between the 2 atoms. That makes what we call a bonding molecular orbital. Or you can combine them out of phase. And when you combine them out of phase, now, remember the orbital will shrink where they overlap. And so there'll be less electron density in between the 2 nuclei and then more on the outsides. We call that an antibonding orbital. Because if you put electrons in it, it will pull the 2 atoms apart. So for H2, simplest molecule you can think of, this is what the bonding and antibonding orbitals look like. The bonding orbital, most of the electron density is between the 2 atoms, or between the 2 nuclei. The antibonding orbital, most of the electron density is outside, so that pulls the 2 apart. So if you want to make a bond, the key is you want to make bonding and antibonding orbitals, but you only want to put electrons in which ones? Bonding. Okay, so that's the main idea behind molecular orbitals. We represent these with these fancy diagrams, which you're not going to be required to do. You're not going to be required to know how to use them. It's one of these things that in the AP curriculum they have like a sentence that's like, molecular orbital theory is a powerful tool for explaining chemical phenomena. And then in the learning objectives it's not there. So it's not something that you're going to be tested on. Although most first year college chemistry courses would definitely include molecular orbital theory. So it's not like, this isn't one of those things where I'm like, oh, I'm throwing this in because I like it. It is in every college chemistry course, except for AP chemistry. But the idea in a molecular orbital diagram is you have your individual atoms on the outsides. So I put the H atoms in green here, and you represent the orbitals in the individual atoms on the outside. So each hydrogen atom has 1 orbital with 1 electron in it, a 1s orbital with 1 electron in it. You combine the 2, and then in the middle you draw a representation of the two molecular orbitals that are made. Anytime you combine 2 orbitals, you need to create 2 new orbitals. So you combine them, you make a bonding orbital and an antibonding orbital. The bonding orbital is called sigma. The antibonding orbital is called sigma star. So anytime you see a star by the name of an orbital, that means it's an antibonding orbital. H2 makes a bond because there's 1 electron in each of those atomic orbitals. So those 2 electrons will both go into the bonding molecular orbital, and there'll be no electrons in the antibonding orbital. Okay, so that's a molecular orbital description of hydrogen. Now when we go to the second row of the periodic table, now we have a lot more orbitals to deal with. You know, hydrogen's really simple because you just have energy level 1, which is just 1 orbital. You go to the second energy level, how many orbitals do you have? Not 2, not 3, 4. You have the S and the 3 Ps. So we get a much more complicated diagram. If I wanted to do oxygen, what happens is we can combine the 2s orbitals, and that'll make a bonding orbital and an antibonding orbital. So those are down at the bottom. And then we can combine the two p orbitals. Now the thing about the two p orbitals is they all point in different directions. So I'll do one set in purple. So let's say my two p orbitals, I have one set that looks like this. Sorry, I said purple and I did blue, didn't I? All right, well. So they have one set of p orbitals that goes up and down. They have another set of p orbitals that goes into and out of the page. So I'm going to draw that like this. And I'm doing that in, I'll say yellow, but it's actually green, just so I consistently mess up the color. So the green ones are going into and out of the page, and then I'll do the last one in chartreuse, which will actually be red. And those are pointed toward each other like this. And I gave this one kind of a wimpy right-hand lobe. Let me fix that. All right, so those are my three sets of p orbitals that I can combine to make molecular orbitals. All right, let's deal with the red ones first. What kind of bond would the two red ones make when they overlap with each other? Since they're pointed directly at each other, that would make a sigma bond. So the two red ones come together to make a sigma bond. And when they make a sigma bonding orbital, they're also going to make a sigma antibonding orbital. So my sigma orbitals come from the p orbitals that I did in red. So the question is, what is an antibonding orbital? An antibonding orbital is the result of combining two atomic orbitals from neighboring atoms, but combining them out of phase. So when they combine out of phase, the result is an orbital that has a node right down the middle, because the two cancel out in that area. And so, all right, follow-up student question is, why would you do that? It's part of the rules of orbitals that when we do these mathematical combinations, we always have to make two new orbitals. So we always have to combine them in both ways. Okay? So just accept that as one of the rules of the math of the quantum mechanics of combining orbitals. Next question. All right, so the question is, the way I drew it, it looks like they'd be in phase. And yes, I would combine them in phase to make this sigma 2p orbital, which would have a big part in the middle and then little parts on the outside. So that's what that sigma 2p orbital looks like. To make the antibonding orbital, I would combine them in the opposite orientation. So I'd combine them this way. So the question is, can you just do that? Like, do they not have a fixed orientation? And the answer is, no, they don't have a fixed orientation. There's a set of mathematical rules that you have to follow when you combine orbitals. And right now, I'll just say, accept it as like part of quantum mechanics. So it's one of those quantum mechanical things that when we combine them in one orientation, we also have to combine them in the opposite orientation. So sometimes you make a bonding orbital and sometimes you make an anti. Well, it's not sometimes you make each. It's you make both. Whenever you make a bonding orbital, you make a corresponding antibonding orbital. So the question is, does it just flip back and forth between the two? No, they both exist. So both the bonding and antibonding orbitals exist. Now, the bonding orbital is low in energy, and the antibonding orbital is high in energy. So the electrons generally occupy the bonding orbital and not the antibonding orbital. So that's why things make a bond, because electrons are in the bonding orbital versus the antibonding orbital. But the antibonding orbital still theoretically exists. And, you know, if and when you take organic chemistry, if it's taught well, you'll see how antibonding orbitals are very useful for predicting reactions, because in a lot of reactions, the first interaction between two molecules is one atom or one molecule's like lone pair of electrons starts to interact with the antibonding orbital of another molecule, and that's how bonds start to get broken. So, the existence of antibonding orbitals, again, all orbitals like don't technically exist. They're all a model that we have created to describe atoms. But they're really useful, and so at this point you just have to trust me that those antibonding orbitals, at least in this model, are there. But they don't have any electrons in them most of the time. But we'll see in this case, some of the antibonding orbitals do. All right, so I combine these two atoms. I make a bonding orbital. I make an antibonding orbital. So my antibonding orbital would look like this. It'll have a big lobe over here, small lobe in the middle, small lobe in the middle, big lobe over there, and a node between the two atoms. So that would be that sigma star 2p orbital. Now, if I combine those two blue p orbitals, what kind of bond are they going to make? Pi. All right. Those blue orbitals are parallel p orbitals, so they'll make a pi bond. What about the green ones? Those are parallel p orbitals. They will make a pi bond. So from the blue and green, we make a pi and a pi star. So the green ones can make this orbital and that orbital, and then the blue ones can make these two. All right. And pi bonding orbitals look kind of like hamburger buns. So if I just draw what the pi bonding orbital would look like, I'll draw this one. It would look kind of like that, where my two nuclei are here and here. And the way I drew it, it looks a little bit like kind of a smiley face with a like a hat or bushy hair on top. I don't know. And then the green one would be going into and out of the page. All right, so the point is, these are the orbitals that we make in this more complicated case where we have all of energy level 2. So for oxygen, we could fill in the electrons there. How many electrons does oxygen have in energy level 2? 6. All right, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, and now I can see my sigma 2s and my sigma star 2s. I have the first 4 electrons are going to go in down there. And then I go up to 2p. Now I have 8 more electrons to put in. So I'm going to put in 1, 2, 3, 4, 5, 6. And now I have 2 left. So they're going to go in up here to these pi star orbitals. So in oxygen, there are 2 electrons in those pi star antibonding orbitals. The way we think about this in molecular orbital theory is we look at how many pairs of electrons are in bonding orbitals, and each one of those we say like makes a bond. Then we look at how many are in antibonding orbitals, and each pair of those cancels out a bond. So if I look here, I have in the 2s 2 in bonding and 2 antibonding. Those 2 cancel each other out. And then from the 2p's, I have 6 electrons in bonding orbitals, and then 2 in antibonding. So that leaves me with a result of 4, a net result of 4 bonding electrons, which would be what kind of bond? A double. Okay, so this corresponds to a double bond. All right, so the question is, how does this relate to the Lewis structure of O2? Lewis structure for O2 that we usually draw looks like this. Okay, it's got a double bond between the 2. And we can see what we call the bond order is, how many bonds there are. Bond order you can calculate by taking the number of bonding electrons minus the number of antibonding electrons and then dividing by 2. So in this case, the bond order is 1/2 times 8 minus 4, which is 2. So the Lewis structure and the molecular orbital diagram both explain that oxygen has a double bond. Now where they differ is the molecular orbital diagram shows that oxygen has 2 unpaired electrons. The Lewis structure does not show 2 unpaired electrons. Some people argue that you should draw the Lewis structure of oxygen with 2 unpaired electrons in it. But that's not an entirely satisfying Lewis structure either. This molecular orbital diagram is often touted as one of the examples where molecular orbital theory explains something that simple Lewis structures can't. Because it turns out oxygen has this property we call paramagnetism. I'm thankful they took this out of the AP curriculum. You don't need to memorize this word anymore. But paramagnetic things are things that have unpaired electrons. And so it'll be attracted to a magnetic field. And the reason I'm glad they took this out, it was just another term people had to memorize, and it's something you don't encounter in most situations. The only reason paramagnetism is important is because oxygen, turns out, is paramagnetic. If you take liquid oxygen and you pour it between 2 magnets, it will just hover there and stay there as it evaporates, because it is paramagnetic. And the molecular orbital diagram explains why it's paramagnetic. So this is one of the pieces of tangible evidence that say, oh, this molecular orbital theory, has experimental support. Rachel? Where are the 4 antibonding electrons? So my antibonding electrons, let me highlight in, gosh, I've used every color. I'll highlight them in, let's say, burnt umber, which is actually going to be orange. So my 4 antibonding electrons are there in orange. Anything that's in an orbital labeled with a star is antibonding. So the question is, do the bonding orbitals fill up first and then the antibonding orbitals? Well, the orbitals fill up from lowest energy to highest. So first it's sigma 2s, then sigma star 2s. So sigma star 2s is an antibonding orbital, but it's lower in energy than the ones from the 2p orbitals because 2p orbitals are higher in energy than the s orbitals to begin with. So it just fills from bottom to top. And again, disclaimer, you don't need to know any of this, but it's still cool to think about, and it's super powerful, and you will want to know it in the future. All right, so on the problem set, the question is, on the problem set we have a problem with helium. So helium, like hydrogen, operates on this simple MO diagram. Okay, how would helium be different from hydrogen? Yeah, each helium atom would have 2 electrons, so both the bonding and the antibonding orbital would be filled. Now, if both the bonding and the antibonding orbitals are filled, is there a bond? No. So that's really what that question is. All right. So if I'm telling you you don't need to know this, why did I tell it to you anyway? Well, what you do need to know something about are semiconductors, okay? And semiconductors can best be explained by relating them to molecular orbital theory. So I'm going to do my best to do that. All right. When you make a big solid, like a metallic solid or a network solid, what you're doing is creating lots of new bonding orbitals and lots of new antibonding orbitals. Okay? So if you consider a solid that's got lots and lots of covalent bonds, you're creating lots of molecular orbitals. So you can see when we go from hydrogen with just 2 atoms and 2 orbitals to then oxygen, which has still 2 atoms but lots of more orbitals, you can see how the picture kind of gets more complex but gets split into a bonding section and an anti-bonding section. So if you look at the oxygen, we have the bottom, that's the bonding section, and then the top, that's the anti-bonding section. When you make a solid where you have lots and lots of atoms, essentially what you do is you create entire bands of bonding orbitals and entire bands of anti-bonding orbitals. So if I take something that's an insulator, like diamond, okay, so here, so in diamond, when you have that big network solid, you're really combining the orbitals of all those carbon atoms to make these big bonding orbitals and then big complicated anti-bonding orbitals. But the key is all the bonding orbitals end up really low in energy. So this down here, what gets called the valence band, these are the bonding orbitals. I can't really see that all that well, but those are the bonding molecular orbitals. And then the anti-bonding orbitals, which are empty, end up here. And there's this energy gap between them. So on the previous diagram, really that energy gap would be the gap between pi and pi star. So I don't have much to deal with in terms of color. What should I go with? Periwinkle. All right. I'll try periwinkle. Let's see if it shows up. All right. So this here is my energy gap. But there's just, one small set of bonding orbitals, one small set of anti-bonding orbitals. In a solid, there'd be a whole band, a whole bunch of bonding orbitals, all with very similar energy, and a whole bunch of anti-bonding orbitals. In an insulator, the valence band gets all filled up. So this drawing shows that all those bonding orbitals are full. So in carbon, remember carbon has 4 valence electrons. And so when you start to put carbons together, basically they have enough electrons to fill up all of those bonding orbitals, but then none of the antibonding orbitals. So you have a valence band with a big energy gap and then a conduction band that's empty. The electrons in the valence band are all just kind of stuck in place. They can't move. Okay? Hence, it's an insulator. When you have a metal, what happens is, because they don't hold their electrons as tightly, this gap between bonding and antibonding is really, really small, and it turns out is non-existent. So in a metal, your bonding orbitals and your anti-bonding orbitals just end up overlapping. So the key is even if you have electrons to fill all the bonding orbitals, there's still plenty of empty orbitals nearby that they can get into to move around. Okay? So here there's no energy gap. This is bonding and antibonding. Or in the parlance of conductivity, they're called the valence band and the conduction band. There's no gap. And so electrons are free to get into these conduction orbitals, these orbitals where they're free to move and move around. So in metals, they're completely conductive. So this would be, for example, I don't know, copper. In a semiconductor, what happens is there's a small gap in energy between the two. So that at room temperature, some electrons from those bonding orbitals actually jump up to the antibonding orbitals. And when they get up here, these are free to roam around. That's why it's called the conduction band. So this is why semiconductors actually conduct electricity better when they're hotter than when they're cold. Because the hotter they are, the more electrons can jump up to the conduction band. Whereas most metals, their conductivity gets worse as they get hotter, because now the motion of the atoms starts to interfere with the conduction. But semiconductors usually have increasing conductivity as temperature goes up, which is different from metals. So the question is, does the energy gap decrease as the temperature increases? No. What happens is the electrons have more thermal energy, so more of them are able to jump over the gap. When you design semiconductors, one way to design semiconductors is to try and make that gap be a target number, right? So depending on the application, you might want a bigger energy gap or a smaller energy gap. So one thing that separates semiconductors would be the size of that energy gap between the two. The smaller the energy gap, the more conductive it'll be. The bigger the energy gap, the less conductive it'll be. Okay. Question? Okay, so the question is, how do the antibonding orbitals actually exist if they're only defined by containing electrons? And the answer is the same way any other orbital exists, even when it doesn't have electrons in it. So when we look at emission spectra from different elements, what we're seeing is electrons that have been pushed up to higher energy orbitals and then are falling down. Well, those higher energy orbitals must have existed in order for the electrons to jump up there. So there has to be, they are there available for the electrons. So they are, essentially an orbital is just a quantum mechanical state in which an electron can exist. And so that state is there even when there's no electrons in it, but it's available to the electrons. I need to pause because the battery on this is dead. Okay. So we're back. So semiconductors, these are defined by a relatively small gap between the valence and conduction bands. So some electrons, just because of their thermal energy, jump over the gap and are free to move. So they can conduct, but not that well, hence the semi. Now there are ways that you can actually improve the conductivity of a semiconductor. Okay. Two specific ways are to make what we call N-type or P-type semiconductors. And it just so happens that this week, some people won the Nobel Prize for Nobel Prize in Physics for inventing blue light-emitting diodes. And the way a diode works is it's a combination of an N-type and a P-type semiconductor. So, very topical for us to discuss this right now. So what do those two things mean? All right. All right, so another strategy is to add extra electrons. So when you think of semiconductors, what's the first element that comes to mind? What's the first element that comes to mind when you think of a semiconductor? Silicon, right? Silicon Valley. So silicon has 4 valence electrons. 4 valence electrons is the magic number because when you start making all those bonding orbitals, it's exactly enough electrons to fill up the bonding orbitals, but leave the antibonding orbitals empty. So silicon, pure silicon, is a semiconductor with a little gap, like this middle picture here. So this could be silicon, for example. Now what you can do to increase conductivity is to add a little bit of a different element that has more valence electrons. So if you take silicon and you add in some antimony, that has 5 valence electrons. That 5th valence electron is now not going to reside in the valence band. It's going to reside in the conduction band. We call this an N-type semiconductor. The N stands for negative. So here's my valence band, and this is full. And then here's my conduction band. It already is starting with some extra electrons in it because antimony had that extra valence electron. Okay, so we call this N-doped. We've doped our silicon by adding in something else. The other thing you can do, the other strategy, is to add an element that has 1 fewer valence electron. Now when you add that element that has 1 fewer electron, now you're creating holes in the valence band. So in other words, the valence band is not completely full anymore. It has these empty spots. This is called a p-type semiconductor because now there are positive charges, those little holes in the valence band. So now the conduction band is completely empty. Here we have missing electrons. From the doping agent because it has fewer valence electrons. And now the way this conducts electricity is it's actually those holes that move from one place to another. So instead of electrons sliding from one side of the of the thing to the other, it's those holes that move from one side to the other. Those positive holes, hence the name p-type for positive. And diodes work by having an interface between an N-type and a p-type. And so you have the extra electrons from the N-type being able to jump into the p-type, and all sorts of interesting things happen. Question? What? So the question is, how fast do electrons actually travel when they're traveling through a conductive substance? Um, and 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 I don't know the answer. Sam just made up a number. All right, do you have an actual source for that, or? Yeah. The the answer is yes. Electricity travels really quickly, but that doesn't mean each individual electron is traveling quickly. So Nick, who was asking the question, brought up the example of suppose you had a tube that was filled with marbles. If you put one marble in one end, you're going to push a marble out the other end, but every marble only had to move a little bit. And yeah, that's a good analogy. You can also think of it like water in pipes. Like, you have water in a reservoir in Western Mass. I turn on the faucet here, and the water comes out. It's not that water molecules in that instant are traveling from Western Mass to here. It's that the water there is pushing down and pushing the water out that's here. So similar idea. The question is there something to describe that called voltage shift? I have no idea. I'm not an expert in that area, I have to say. So one of the objectives from the AP test, if we look at our objectives, one objective was to compare and contrast n-doped and p-doped semiconductors. It was thrown in there. I don't know exactly what they want you to know, but they want you to know a little bit about what n-type and p-type semiconductors are. Remaining questions? All right, thank you.